Welcome to the solution to the AP Physics Equilibrium problem set, problem number 17. We have a 500 Newton uniform rectangular sign. The word uniform indicates that we can use the center of the sign to be where the weight is located. In other words, whenever you hear that an object is uniform, you can consider its weight to be located at its center. 500 Newton uniform rectangular sign, 4 meters wide and 3 meters high, is suspended from a horizontal 6 meter long uniform 100 Newton rod as shown in the diagram below. The left end of the rod is supported by a hinge and the right end is supported by a thin cable making a 30-degree angle with the wall. A, find the tension T in the cable. B, find the horizontal and vertical components of the force exerted on the left end of the rod by the hinge. All right, let's start with a free body diagram here on our drawing. We have the weight of the sign in its center, straight down, and that weight is 500 newtons. We know the value, so we'll label it right on our diagram. Note that that weight, if the sign is 4 meters wide and it looks like the end of the sign is on the end of the beam, is 2 meters from the cable. The rod itself is 6 meters long, and it's uniform, so its weight in the center, 3 meters from either end, is 100 newtons. Okay. We also have the tension in the cable. T is labeled. And we're asked to find in B the horizontal and vertical components of the force exerted on the left end of the rod by the hinge. So we'll call that Hx and Hy. We also know, even though these aren't actual forces, that we'll have to take into account Ty and Tx. That's Tx and Ty. Okay? Now, as we look at what they're asking us to find here, the issue in this problem, as we've outlined in other problems, is that we have two unknowns in the vertical plane, and we have two unknowns in the vertical plane, and we have two different unknowns in the horizontal plane. So this is not solvable by summation of forces. So to solve for the tension in the cable, what we're going to do is we're going to summate torques. In order to summate torques, that means we're going to have to select a pivot point. Well, we want to intelligently select that pivot point. If we're solving for the tension, then we want to select the pivot point to be at the hinge to eliminate Hy as causing torque in a torque summation. Hx doesn't cause any torque because it's parallel to the lever arm, so it has no component perpendicular to the lever arm. So we wouldn't have to worry about that anyway. And Hy is perpendicular to the lever arm, and by selecting that as the pivot point, we eliminate Hy from causing torque because there's no lever arm distance. All right, so we're going to start with A by sigma tau equals 0. And let's see what we would have here. Before we continue, I want to be clear that Ty, how would we calculate that? And given where the angle of 30 degrees is, the given angle, it would be T cosine of 30. And Tx would be T sine 30. And that's Tx. All right, kind of getting myself jumbled up here, so I'm going to erase that and start down here, or below here, the diagram. Let's restart A here. Sigma tau equals 0. And so we're going to start from the pivot point and work our way to the right, away from the pivot point, considering each force as we go, individually causing torque. And the first one we come to is the 100 Newton weight of the rod. What is the lever arm distance of that 100 newtons from the pivot point? The center of the rod would be 3 meters away. By itself, it would cause the rod to rotate clockwise around the pivot point, and so that torque would be negative. Next, we have the 500 Newton weight of the sine, and from the pivot point, if the sine is 4 meters wide and at the end of the rod, that means it's 2 meters from the right end, therefore 4 meters from the left end, so the lever arm distance from the pivot point is 4 meters. It also by itself would cause the rod to go down and rotate clockwise around the pivot point for a negative torque rotation. Our next force perpendicular to the rod, to the lever arm, is the Ty component. And that Ty component, as we just mentioned, is T cosine 30. T cosine 30's lever arm distance would be the full length of the rod, which is 6. By itself, it would raise the rod upward in a counterclockwise rotation, and therefore that is positive torque rotation. You can see the advantage of doing this is that we only have T as an unknown in this equation, and we can solve for the tension. I'm going to point out at this time, it is so important to take your time and take each force one at a time, figure out its lever arm distance and its sign, because if you make one mistake, either in a lever arm distance or in a torque rotation sign, ball game over, you will not get the correct answer. Okay, so it's really important that you go methodically through and come up with a system that works for you. Solve this for T. Go ahead and stop the video and calculate if you need time to. And you should get 443 newtons. Okay? All right. Now that we know the value of the tension, we can do summation of forces in order to figure out the Hx and the Hy value. It doesn't matter what order we go in here. For B, let's do the horizontal components because there's less of them. It would be easy. Sigma f in the x direction equals 0. The summation probably would look something like Hx minus T sine 30. But since there's only two forces there, we can simply just set them equal to each other. T sine of 30 degrees. We sub in our value of the tension we solved in A. And that looks to be a value of 222 newtons, which makes sense. It's half. Sine of 30 is 1/2. So to 3 digits, 222 newtons. Hy has a few more forces in that direction. Sigma f in the y direction, also 0. What do we have here? We have Hy up. We'll call that up direction positive. Plus the 443 cosine 30. That's your T cosine 30 is also up. Minus how much total force do we have down? It would be the 100 plus the 500 newtons down for a total of 600 newtons down equals 0. We go ahead and solve for Hy. And we should get 216 newtons to 3 digits. One thing I'm going to point out to you here is a common mistake by beginning students doing problems that involve both summation of torques and summation of forces is that they, on accident, include multiplying by lever arms when now summating forces. Be careful to not do that. Summating forces, there's no lever arm, it's just forces. You only include lever arms when you summate torques. Okay. All right, if there's any questions on this problem, make sure you ask in class tomorrow. And we'll have more practice on problems that have a combination of both summating torques and summating forces when we tackle numbers 18 and 19 in class tomorrow.